We are going to have Winnie come up and do this on the board. I think I got this. Yep. So while she's writing, notice that the table says concentration at time t. That is some time during the reaction, but not when it is before it has reached equilibrium. Sorry, I'm just losing it today. So that can be any time in the reaction that we have measured those concentrations. It is probably not at equilibrium, although if Q was exactly equal to K, then it would be at equilibrium. We've been given K sub C, for this reaction, 5.10. Okay? And actually, it specifically says it shows non-equilibrium concentrations. So this is concentrations measured at a time before we've reached equilibrium. What direction is the reaction going to go? Is it going to go to the right, favor the forward reaction, or go to the left, favor the reverse reaction? So, thank you very much. So it is going to go to the right because our Q is 4.1, which is less than our K, which is 5.1. If Q is less than K, we have not yet gotten to equilibrium, and we're going to be favoring the forward reaction. If Q was greater than K, then we would be favoring the reverse reaction. We would have more products, and we would be pushing towards the left. Okay, so favoring the forward reaction means proceeding to the right. Favoring the reverse reaction, we call it proceeding to the left. So this one is going to go to the right from this point in time where we did not have equilibrium yet. Okay, until Q equals K, and then it's going to hang out there, and we're still going to have the forward reaction and the reverse reaction happening, but they're going to be happening at the same rate, and we're going to have constant concentration, right? Okay. So that takes us into what I call the fun part of equilibrium, which is Le Chatelier's principle. This is the FAFO of chemistry. This is the, we're going to mess things up. We're going to go in and mess things up, and then we're going to see what happens, okay? And we're going to be able to predict what's going to happen based on what we know about the equilibrium constant, what we know about the reaction, et cetera. So the principle, a statement of the principle is that when we have a system that is at equilibrium, but then that system is subjected to change, the system is going to respond to minimize the effect of that change. So if I jump on the trampoline and I push the rubber of the trampoline down with the weight of my body, it's going to respond by pushing back up on my body and throwing me into the air. Okay, that's kind of what's going on here with Le Chatelier's principle. I put the word homeostasis on this slide because if you're a biology person, you probably know what that is. That's the processes by which we keep a lot of our properties within a narrow window. So our body temperature needs to stay within a narrow window in order for enzymes to function optimally, and probably a lot of other things as well. So our pH levels in our blood also have to be at a certain level. There's lots of other things about our bodies that are kept within a certain level in order, and if it goes up, then the body works to push it back down. If it goes down too low, the body works to push it back up. Sort of like your thermostat at home, that if it gets too hot, the AC clicks on, takes you back to your set point. If it gets too cold, the heat clicks on, takes you back to your set point. This is a little bit different because you're not going to go back exactly to the same set point. You're going to shift the equilibrium in one direction or another. But we are going to go back to equilibrium eventually, and that shift is going to be in the direction that's going to counteract whatever the perturbation was. Okay. So here are some things that we can do to mess with our equilibrium system. We can change the concentrations. So I can have a system that is happily sitting at equilibrium, and I can just dump in some more reactant. And now it's not at equilibrium anymore, but it's going to shift to make up for that. I could dump in some more product. I could remove a reactant or a product, and the system will have to shift to compensate for that. Okay. Similarly, if we have a system with gases, then changing the pressure is also going to shift the equilibrium a little. Changing the temperature can shift the equilibrium. And adding a catalyst, we'll talk about specifically what that does to the equilibrium. But we can, some of these are going to shift to the right or to the left, depending on which direction we're going in. In some cases, they're not going to have any effect at all. And so we want to know what's happening. What we want to be able to predict, if I raise the temperature, where is the equilibrium going to shift? And in any given reaction, or if I dump in more reactants, how is that going to shift the equilibrium? So one reaction that we talk a lot about with equilibrium, and specifically in terms of Le Chatelier's principle, is the Haber process. So this is formation of ammonia from nitrogen gas and hydrogen gas. This is an incredibly important reaction, and the way that Fritz Haber used essentially Le Chatelier's principle to drive the forward reaction so that he could make more ammonia is pretty much the reason why we are able to feed most of the 8 billion people on Earth. Because if we didn't have fertilizer, then we wouldn't be able to do that, artificial fertilizer. So bacteria in roots of plants fix the nitrogen out of the air into a way that plants can use it. Plants cannot use the N2 straight out of the air as a source of nitrogen. So what we are able to do once we make the ammonia, we can turn that into other things. Unfortunately, we can also turn it into bombs. So Fritz Haber doesn't have, necessarily the shining halo or anything, because it kind of went in both directions, and he wasn't a particularly nice guy. But regardless, his ability to figure out how to make this process, this reversible reaction, produce primarily the one forward product, is crucial to us being able to live right now. So, if we change the concept, one of the things that we can do to make more ammonia is, once we reach equilibrium and the forward and reverse reactions are the same, we can take some of the ammonia out. We can selectively remove the ammonia from the tank. Once we do that, we've lowered that concentration, and now our reactants are going to compensate for that by making more ammonia, because our concentrations will be out of whack with respect to our equilibrium constant. So whatever we do, the system is going to compensate by shifting it to make up for that, to compensate for that. So if we remove or decrease the amount of ammonia, the equilibrium system is going to shift to make more, to make up for the fact that we took a bunch out. If I continually add a bunch more nitrogen, then when it's at equilibrium, then also the equilibrium will shift so that I consume some of that extra nitrogen that I just added. And so we'll end up taking some of the hydrogen that's floating around and making more ammonia that way. Okay. So whatever we're removing, it's going to try to make more of. Whatever we're adding, it's going to try to use up to make the stuff on the other side. Okay. This is an example on page 14 of a graph that you might be asked to interpret. And I will give you guys some other examples of graphs to look at tomorrow. But the idea here is this is concentration versus time. At time 0, between time 0 and time 10, we are at equilibrium. How do we know that we are at equilibrium? Just looking at the graph, how would you know that you were at equilibrium between time 0 and time 10? Yes, the concentrations are constant. So the rate of the forward reaction, the forward reaction is still happening. This is not static. Forward reaction is still happening, the reverse reaction is still happening. But they're happening at the same rate, so we're not seeing any change in the concentration of the reactants or the products. So when you have a concentration graph, when the concentrations are flat, that is at equilibrium. And it's just gonna hang out there with the forward and reverse reaction still happening, but at the same rate. At time 10, we add a bunch of H2. So this is the reaction that we're looking at, hydrogen gas, iodine gas, combined to form hydrogen iodide, okay? And we have this lovely system just chugging along at equilibrium, and then we dump in a bunch of hydrogen. The way that you recognize that this graph is about the experimenter changing the concentration is that it's an immediate change. It's a spike. It's not a gradual change, okay? If you see a graph with gradual changes, that means something happened that wasn't a change in concentration, but the system is responding to that other thing, some of the other stuff that we'll be talking about. Okay, but if you see a spike up or down, that is the perturbation that happened, okay? So in an instant, we've suddenly given ourselves more H2. Well, the system is going to react by using up that H2, or some of that H2 that we just dumped in, right? So what we're going to see is the equilibrium shifting to the right and decreasing the concentration of H2. Also, because of that, decreasing the concentration of I2, the other reactant, and increasing the concentration of the product. Okay. And then, at some period of time, we reach a new equilibrium, where again, by time 15, we have reached that new equilibrium, and our concentrations are once again constant. So this is typically what you're going to see for something like this. You'll see equilibriums happens, a change happens, and then something changes to bring it, the system changes to bring it back into an equilibrium state. It's not bringing it back to exactly where we started. It is still in equilibrium. The concentrations have shifted a little bit. And our Kc is actually the same. Okay, our Kc is going to be the same. This graph doesn't show that as well because it shows all of our H2 getting used up there, and it's like the scale on here isn't exactly perfect. Well, there's no scale, but the size of the curves or whatever, like don't take that to mean what's going on, because yes, we are ending up with less of our reactant, but we added more of this reactant first, and then we came down. So we don't have a net decrease in our reactants. Okay, so the concentration of products over concentration of reactants is actually not going to change. So the system, that is a constant at a particular temperature. So the system is going to change to make that Kc still a constant, even though we've added something or we've taken something away. Okay. All right. So we just talked about this. So the equilibrium is going to shift towards the product in favoring the forward reaction, and we call that shifting to the right, as opposed to shifting to the left, which would be the reverse reaction. Value of Kc does not change. Okay. So this shifts to the right. I think if you said towards the products in an answer on the test, they would give it to you. Kc does not change. Okay. What's going to happen if we add HI? Go ahead, Kathy. Yeah, it's going to shift to the left. All right, so if we add more stuff over here, it's going to shift to get rid of some of that stuff. If we add more stuff over here, it's going to shift to get rid of some of that stuff. It's always going to counterbalance whatever the perturbation was. Okay. Okay, let's talk about pressure. This is only going to be an issue if you have gases in your reactants and products. So definitely pay attention to the state symbols if you're given a reaction. Say we have a system where we have A turning into B and vice versa. So this is a simplification. And we have an initial volume and initial pressure. But the equation says that we need 2 A's to make every B. So we have 2 moles of gas on the reactant side and 1 mole on the product side. Okay. If we increase the pressure, that's going to basically make it's going to increase the concentration. It's going to make all of the particles closer together. And so the system is going to react to that by trying to free up space. And it's going to free up space by moving to the side where there are fewer moles of gas. Because when we're talking about the amount of a gas, we're not talking so much about the volume that a particle takes up, but how much space it's moving around in. That's what the pressure is, the collisions against the particles on the sides of the container. So if we're going to have more collisions in this higher pressure state, the system's going to react to try to reduce that. It's going to do that by driving the reaction in the direction of fewer moles of gas. If we expand the tank, we decrease the pressure, then the system is going to move in the direction of making more moles of gas to try to bring the pressure back closer to what it was earlier. Okay, so more moles of gas in the same space is higher pressure. So if we increase the pressure, the system is going to try to decrease it. If we decrease the pressure, the reaction system is going to try to increase it. Right? And this is another example from our Haber process where the reactant side has 4 moles of gas and the product side only has 2. So this reaction is often done at high pressures because at high pressures, it's going to drive the reaction towards the formation of the ammonia. So it's another thing that we can do to increase our yield of ammonia. That's not always necessarily what we want to do with a reaction, but in this case, it's a way that Fritz Haber developed the technique so that we could make as much ammonia as possible. Okay, so on page 15 of your study guide, we've got carbon monoxide reacting with hydrogen gas, and we're going to make methanol. It's kind of exciting. If we increase the pressure, what's going to happen? What direction is the equilibrium going to shift to? So we're increasing the pressure. The system is going to change to try to relieve that pressure, to try to lower the pressure. Anybody? So when we're talking about pressure, you're looking for anything that has a G, and you're counting the moles. So we've got 3 moles on the reactant side. We've got 1 mole on the product side. If we increase the pressure, we are going to shift towards fewer moles because those particles are going to take up less space. Even though the particles themselves are bigger, they're so infinitesimally small that it doesn't really, the volume of the particle doesn't have much of an effect on the pressure. So having fewer particles decreases the pressure. Okay? So we're going to shift to the right. If the pressure is decreased, we're going to make some more moles of gas and shift to the left. Okay. So that's concentration and pressure. Temperature is a little bit more complicated. So we can't just look at the reaction, the chemical equation. We have to also know what's the delta H for the reaction. Is it endothermic or is it exothermic? Okay, because it's going to have the change in temperature is going to have a different effect depending on whether the equation is endothermic or exothermic. And I'm going to do this demo for you guys tomorrow. But this is a reaction where we have N2O4 reversibly turning into 2 molecules of NO2 or 2 moles of NO2. It goes back and forth. What are you looking for? I think Binta left them on the note card. Could you put them on by the, yeah, thanks. The way I like to think about changes in temperature and Le Chatelier is I think about the heat being either a reactant or a product. Okay? So if we have an endothermic reaction that is absorbing heat, then we can write heat as a reactant because that is going into that equation, that forward equation. Okay? If we have an exothermic reaction, we can write heat as a product because the heat is being generated by that reaction. Okay? Once we do that, now we can think about changes in temperature as adding or removing heat. And then heat becomes just like another reactant or a product, and we can think of it the same way that we think about concentration. Okay? So if I add more N2O4, then I'm going to drive the reaction to the right. If I add more heat, I'm also going to drive the reaction to the right because the system is going to respond by trying to lower the heat. It's going to lower the heat by using some of that heat to make the NO2. Okay? If I lower the temperature of a endothermic reaction, then if I lower the temperature of the system, then it's going to drive back the other direction because it wants to generate heat to counteract that lowering of the temperature, that loss of heat. Okay? Obviously, it's the opposite if it's on the exothermic side. So if the heat is being produced by the reaction, then increasing the temperature is going to drive us back towards the reactants. Decreasing the temperature is going to drive it forwards. Okay? So think about what, if you're given information about temperature change, you will probably be given information about the enthalpy change. And possibly, you will have just calculated the enthalpy change in part B, and this is now part C. It's asking you what's going to happen to this reaction when we increase the temperature. All right, so that's the kind of thing they like to do. Okay. This is the only thing that we can change that changes the value of the equilibrium constant. Okay? Changes in concentration and pressure will not change Kc, but changes in temperature will. So you usually see in a question, like our warm-up question, it said specifically the Kc at 527 degrees Celsius or whatever it was is this, because you have to specify at what temperature, because temperature will change the equilibrium constant. That's the only thing that will change it. Okay? And you can think about that in terms of the Maxwell-Boltzmann diagram. So if we have increased the temperature, we're increasing basically the number of particles that are available to do that reaction that are over that activation energy. And so that's why we're going to be able to shift the value of Kc. Okay. Okay, so this one's not in your study guide. Let me see if there is one. Yeah, let's look at the ones in your study guide. Page 16. There are several reactions. Let's look at the first one. So we want to know, here's this reaction. We don't even know what it is because there's X in there. Like, it doesn't even matter, okay? All we know is that it's reversible and that our delta H is negative 50. So if we have a negative delta H, what does that mean? It means it's exothermic, okay? If delta H is negative, that means we've got a situation where we started reactants at a particular temperature and we ended at a lower temperature, and that delta H, that change in temperature is negative, and we are releasing that energy. That difference in energy gets released as heat. Okay? So where are you going to put heat if you're going to add it to the equation as either a reactant or product? What side is it going to go on? Reactant side or product side? Yeah. Product side, yep. We're releasing heat. It is a product of the reaction. Okay, so we're going to put plus heat. Okay. Now we're going to decrease the temperature. It was at equilibrium, and now we put it on ice. What direction is the shift going to take? Are we going to shift to the left, shift to the right? Where are we going to shift? So we decrease the temperature, which is like removing a bunch of heat, okay? If we stick it on ice, that heat is going off to melt the ice in the ice bath, right? It's going away from the system and its immediate surroundings, right? So we're essentially losing heat. Which way is the reaction going to go? Forward or reverse? Or to the right or to the left? Anybody? Yeah. It's going to go to the right. Yeah, because we're losing heat. The system wants to counteract that by generating more heat. We generate more heat by driving the forward reaction. Okay? Because that's what gives us more heat. So we're going to drive that. Now, we're going to drive it that way. What's going to happen to KC? Is it going to get bigger or smaller? Remember that KC is oh, sorry, I did that wrong. Gosh, I got to stop. KC is products over reactants. So is KC going to go up or down? Are we making more products or are we making more reactants? We're shifting this way, right? So we're making more of the forward reaction products, okay? And so that means that KC is going to go up because we have a higher concentration of products, lower concentration of reactants, and it's not balanced out by any perturbation in concentration that we did. Our perturbation was temperature, not concentration. So we're having overall an increase in the products and a decrease in the reactants. And so that's going to make KC will increase. Okay. Okay. What about a catalyst? Catalyst changes the activation energy, right? It decreases the activation energy, makes that hump a little bit smaller. What happens to the activation energy of the reverse reaction with the catalyst? So think about the reverse reaction. We're starting down here. We're going up here and coming down. So it decreases the activation energy for both, in both directions, okay? Because it's the same hump, no matter which way you're going on the energy diagram, okay? So the activation energy is going to be bigger in this case for the reverse because that's endothermic, but it's going to be smaller than it would have been without a catalyst, okay? So both directions are going to increase the rate of reaction to the same extent with the catalyst. So we're not changing Kc. We're not changing where equilibrium is if we dump a catalyst in, okay? All we are changing is how quickly we get there, because the rates of both reactions are going to be faster, so we're going to just get to equilibrium sooner with a catalyst. Now, if we're also changing all these other things in order to make our ammonia or whatever, that's still going to give us a boost when we throw a catalyst in. And so we do have usually a nickel or carbon, I forget. We can watch that video another time maybe. That's used in that reaction. But yeah, so if we want to make a particular product, we can change all of these things. We can set up our system to try to take advantage of all of these changes to drive the reaction the way we want it to go. Okay. That was, wow, last year. Right. So I think that I'm going to leave. Yeah, the next thing we're going to do is look at some graphing questions. So we'll do that tomorrow. And I will leave you here.